All right, so let's begin with what we're talking about today. Today we're going to be pushing forward and we're going to be discussing the law of large numbers and give you a basics on central tendency. Begin with the law of large numbers. I begin with a coin. What coin is this, for those who can tell? Marvin, what coin is this? It's a quarter. Right? So this is a quarter. What are the sides of a quarter? Heads and tails. Now a trick question. You guys are really quiet. That's kind of weird. That's okay. So yeah, this is a fair coin. A fair coin means it's not weighted in any way. It doesn't have like two heads or two tails. It is one side head, one side tails. What do you think are the chance of getting the heads? What do you think is the chance of what's the play over here? What do you think of the chance of getting heads? 50%. Why do you say 50%? The two sides of a coin, right? Simple mathematics. It's a 50% chance. Instead of 50%, right? Well, what do you think the actual? There's a difference, though, between the theory and the practice. There's a difference between mathematically and logically what we think will happen and what actually happens, what empirically happens. What do you think I mean by empirically? Anyone? What does empirically mean? Yeah?
Empirical means observed.
Exactly, Julia. Right? Empirical means observed. In other words, it's the actual data. So, gathering a sample, for example. So that's what I'm going to do, right? I don't know, maybe I said it's fair, maybe it's not fair, maybe I'm lying. Let's find out. What'd I get? All right.
Heads.
Heads. I got heads.
So, we said that it was a 50% chance tails, 50% chance heads, but empirically, is the empirical average. Right. Empirically speaking, I got 100%. What do you mean? What'd you say?
Flip it again.
Flip it again. In other words, right, so immediately it's like, well, it's not possible to get 50% if you only flip it once. Right. This is n equals 1. What does n stand for? Yep, number of times you flip. Or generally speaking, the number of observations. Right. N is the number of observations. That notation of n is going to come up many, many times in this course, so it's good to get used to it. Whenever you see that lowercase n, think that. Okay, fine, fair enough. What'd I get? Tails. Hey, it worked. So. Is the new empirical average n equals 2. What were the chances of me getting heads that second time? What do you think? Like, is it possible that I could have gotten heads again? Yeah, it's possible. But I didn't. I got tails. So does that show that the theoretical average is right? Does that prove that the theoretical average is correct? Yes or no? Yes, why do you say yes?
Because from the observation, there's two, I guess, like there's only two options you can get out of all of the options, which is 2, and therefore it's a 50-50 chance, which is a theoretical option. I mean, the chance as well. So
we have to be careful, right? We don't want to say true, because that sounds kind of final. but you're right that this seems to have evidence for. That said, let's think about all the different possibilities we could have had. So it could have been heads or tails, right? And this is the first flip right here. This is what's called a tree diagram. We're going to do a lot of these in the last unit. But for now, it's a simple, straightforward thing. If we get heads, we can flip heads or tails in a second. If we get tails, we can flip heads or tails in a second. So this is sort of a different possibilities paths we could have taken. So our options are heads, 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 tails, tails, heads, tails, tails. What are the chances of each of these paths, of each of these sequences? It's what? 25%, right? There's an equal chance of heads or tails every time. Right? This is according to our theory. And so that means this is 25%, this is 25%. There's 4 chances, they're all equally likely. So what are the chances of me getting heads, heads? 25%. Right? In fact, the chance that I get some empirical average that matches the theoretical average is about 50% chance. I could have gotten heads, tails, or tails, heads. Each one of these would have matched it. There's half the possibilities. But there is a 25% chance I way overestimate, and there is a 25% chance I way underestimate. In other words, I have a 50% chance of being right. And a 50% chance of being really wrong, of being way off. Not merely a little bit off. Oh, I thought it was 40%, or I thought it was 75%. We're being way off. A 0% chance, or a 100% chance. So even though I got the quote-unquote right answer in this example, and I don't always when I do this, sometimes I get 2 heads in a row. Sometimes I get 2 tails in a row. Sometimes I do get 50% chance. That is no guarantee. Is it possible to make it a guarantee? Is it possible to flip it enough times that definitely at the end of all those flips, I will have exactly 50% heads and 50% tails? Guarantee. It's very, very unlikely that I'll get the right answer. I'll get that theoretical result, but it's not guaranteed. If I decide to have flipped it 4 times, these are all the possibilities of what would have happened. I could have gotten only heads. I could have gotten only tails. I could have gotten a mixture of heads and tails, right? In all likelihood, I would have gotten a mixture. Some of these, exactly 6 of these, matches my theoretical average. But some of them don't, right? There are 4 right here that do not, that are too low. There are 4 right here that are too high. And a 50% chance of extreme wrong, a 50% chance of correct when n equals 2. Here, what are the chances of extreme wrong? And by extreme wrong, I define it as either 0% or 100%. What are the chances of extreme wrong? Dennis, how many options are there for extremely wrong? 1, where'd you get 1 from?
0.
So 0 is extremely wrong, but you know it's also extremely wrong? 1, right, 100% chance. So how many options are there? 2, and how many different possibilities do we have? Think I heard it? 16, right? There are 16 possibilities. 2 are really wrong. So that means we have a 2 out of 16, or if you want to simplify that, a 1 out of 8. What are the chances of being sort of wrong, either 25% or 75%? How many different options are there? There's 16 total options, but how many ways are there to get to sort of wrong, either 25 or 75%? 8. So 1/2, or just so that we keep the denominator the same, we'll just make it 4 out of 8. Being somewhat wrong. And what are the chances of being exactly right? 6, or 6 out of 16, or 3/8, right? And note, of course, these all add up to 1, right? 1/8 plus 4/8 plus 3/8 is 1, which makes sense. Appreciate what happened when we increased our sample size. When I was doing it n equals 2, we had a 50% chance of being correct, spot on, but we had a 50% chance of being totally off. When I increased my sample size to 4, yes, I'm slightly less likely to be completely correct. It went from a 50% chance to a 3/8, a little bit less. I think that's a 37% chance. But I went from a 50% chance of being extremely wrong to only a 1/8 chance of being extremely wrong. So this is a huge, in general, is an improvement. As I increase my sample size, I will tend to get closer to the theoretical mean. And you see this when I increase my sample size to 10 coin flips. This is the distribution for 10 coin flips. You see that these really like 100% chance of getting what's it called? Heads, or a 0% chance of getting heads are vanishingly small. That's a very small likelihood. The vast majority of the chance is right here in the middle, right? With exactly 50% being the single most likely result. Yeah.
So with n equals 4.
N equals 4, because you can't have 50% chance if you're only flipping 3. So I went from n equals 2 to n equals 4. Right. I'm gonna write it down, because this is what we call the law of large numbers. As you increase the number of observations, the empirical mean will tend to approach the theoretical mean. And I'm going to underline the words tend to. It will tend to approach the theoretical mean. It won't guarantee, as we know, there was a chance that we went from, I flip it 2 times, and we get exactly the distribution that I would expect, 50%. And then I flip it 2 more times and I get 2 tails in a row. And now I went from 50% from 1/2 chance of getting tails to empirically a 1 1/4 chance. I'm sorry, a 1/2 chance of getting a heads to a 1 1/4 chance of getting a heads. So it's not a guarantee, it's just a tendency. Questions? Great. Let's talk about roulette. How many of you know what roulette is? Anyone? Sorry, I'm looking for my eraser. How many of you know what roulette is?
Would you try to guess the number that the dice or the thing falls on when you spin the wheel?
Mm-hmm. So it's a wheel, right? It's a wheel with how many spaces on it? No. Anyone know? 38 spaces if you're in the U.S. 37 if you're in Europe. That 38 spaces consists of 18 red, 18 black, and 2 green. European wheels only have 1 green. But America likes to throw off the probabilities a little bit. It's a nice even number. The greens, by the way, are 0 or double 0. So, has anyone ever seen a roulette wheel in action? It's a movie, but I'm talking like in person. It's easier in person. No, I haven't seen it in person. So if you ever go to a casino, you will see the roulette wheel. They put the ball in, they spin it, they run it along the side, and then they spin the roulette wheel, and then it essentially falls on one of them. And people place their bets before it finally lands. There's a point where you can't place any more bets, because then it becomes pretty clear where it's going to land. Now they will have next to that roulette wheel a digital display of the numbers. Sometimes they display it as these are the numbers that just rolled. Sometimes they display it as these are the numbers that it's been rolling a lot, and these are the numbers that it hasn't been rolling very often. These are the colors that's come up a lot. These are the colors that haven't come up very often. Why do you think they do that? Yeah.
Because people make an emotional attachment to that, even though it's not logical. Even if there's any random possibility that any color would come up, they tend to sort of believe either if a color's come up a lot, maybe it will come up a lot more, or if it hasn't come up, we've seen it come up, then they kind of believe the odds.
Ah, yes, this is they're trying to game it, right? I like how you say it. That they will try to interpret that information in 2 different ways.
It's like the same reason people like request a lottery number, even though
There's no impact at all, yeah. There's no such thing as a lucky lottery number, exactly. Absolutely right. So, but I like how you did it in 2 different ways, though. You said some numbers are more, they see the numbers as coming up, so they consider them to be more likely to come up. And they see numbers as not coming up, and they see those as more likely to come up. And that reflects 2 different fallacies that we have when people try to apply. One is when people try to apply the law of large numbers, and one is just related to that first fallacy. So let's start with the first fallacy, because I literally had this conversation with an economist once at a conference, and we went through the casino area, because I think it was at Vegas, and we went to the casino area, and he looked at the roulette wheel, and he saw those numbers displayed. He's like, oh, those numbers are due because of the law of large numbers. The law of large numbers says that as you keep increasing your number of observations, the spins of the wheel, then it should approach the theoretical average. Theoretically, each result, each number, each wedge of that wheel has a 1 in 38 chance of coming up, right? 38 options, each one equally spaced, 1 in 38. So if this hasn't come up in the past 50 or 60 spins, then it is due, because that's what the law of large numbers says. And I'm like, that's wrong. Shame on you. Because of what you said, right? He is succumbing to what we call the gambler's fallacy. To understand the gambler's fallacy, we should first define something else, an independent trial. What is an independent trial? Yeah, exactly. In other words, the outcomes of the current trial are not influenced at all by the by previous outcomes. Chance of future outcomes. Outcomes of previous trials. A trial, by the way, is just any description of an event that has some sort of probability attached to it. We're spinning the wheel, we're flipping the coin, whatever it is. So the gambler's fallacy you probably have heard in independent trial before. The gambler's fallacy is believing that I'm having a hard time today. Hold on. Underrepresented outcomes are more likely in future independent trials. In other words, each spin of the roulette wheel doesn't change, doesn't influence any future spins. So if you keep getting red or you don't see a lot of green, that doesn't mean that red is less likely in the future or green is more likely in the future. The roulette is just a wheel. It doesn't know what it's done before. It's not trying to balance out the universe. It's just spinning the damn ball. August 18th, 1913, Monte Carlo, famous gambling place. The roulette wheel, there's a roulette wheel that people have started gathering around because it resulted in black like 12 times in a row. And what do you think people are doing when they see black 12 times in a row? No, you're thinking of something else. You're thinking of something we're going to talk about next. They're typically thinking in terms of this. They're seeing how it should be, it's a little less than 50% chance black, 50% chance red. So they see black 12 times in a row. What do you do? What do you think people do?
That's not choose black.
You don't choose black, right? You choose.
The underrepresented.
Mm-hmm. Typically they went for red, right? They kept betting on red. They said, oh, 12 times in a row black. Let's bet on red because red is due. They always use that. They always say due, like it's a train or something that's coming in. And so people started putting a bunch of money. It spun for a 13th time, and for that 13th time in the row, black again. And what did people do? They bet on red again. This time it's going to happen. And then it became black again. Okay. So 14 times in a row, fine. But red is definitely due now. Put more money on red. 15 times in a row, black. Spin it again, black. 16. 17, black. It continued to get black 26 times in a row. People lost millions betting on red. It's a real thing, right? The reason why the casinos display these numbers is people want to get that sense of control. Yeah.
Did anyone bet on black that day?
I
house.
I would, yeah, right, the house did. The house bet on black that day. It did really well. So, don't do that. Yeah.
So I'm confused though, because, so you said your economist friend, you were annoyed because he said, well, by the law of large numbers, it should come eventually. But isn't that kind of what the law of large numbers is saying? Like, not 26 blacks in a row, but if you spun a roulette wheel like 3,000 times, and it was always spinning black, then wouldn't that be an indication that either the wheel is rigged or that at some point red has to come up to get to that theoretical mean of a 50-50 chance?
I'm glad you asked that question. Let me.
How many is enough to be like, this is a big enough trial that something needs to change?
So this kind of goes back to what we were talking about before, when it's like, what's a big sample size? And it's like, there's no hard, fast rule on what a big sample size is. We sometimes say 30 because people want a number, and so that's, I don't know, 30. But there's no hard rules. You sort of have to, I mean, like, if it gets black 26 times in a row, you might want to look at it and see if there's something wrong with it. But you have to recognize that it is possible for that to happen. One thing we're going to be doing later in the class is going deeper into the statistics, because you're sort of hinting at what a big thing stats is about. When you see something happening that's weird, is that weird because there's something fundamental going on that you should pay attention to, or is it just random? And so we'll talk more about how to unpack that and mathematically determine, or at least get an idea for maybe it is, maybe it's not. But a different way to answer your question is to ask you a different question. Consider two sequences. Here is a sequence of black, 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 100% black. Here's a sequence of black, red, red, black, red, black, black, red. 4 reds, 4 black, 50% chance of black. Which one of these is more likely to occur? Number 1 or number 2? Number 2, how many of you say number 2? Raise your hand if you think number 2 is more likely to occur. How many think number 1 is more likely to occur? What's the answer? Does everyone want to guess? Most of you think 2 is more likely to occur. 1 or 2 of you thought 1 was more likely to occur. But
so I guess it depends on your asking. If you're just asking, is it more likely that black or red comes out 50% of the time, then yeah, that's more likely. But if it's that exact sequence, then there's the same likelihood.
Julia's hitting the nail on the head. It says a distinction between what the aggregate result is and what the sequence is. These sequences are equally likely. They are equally likely sequences, right? There's a 50% chance of black, and a 50%, slightly less than 50%, but just whatever. 50% chance of red, 50% chance of red, you know. That sequence is equally likely. The thing is, with this 50% chance, there are more paths to 50% in aggregate, right? You could also get 50% by doing this. That's also a 50% chance of getting black and 50% chance of getting red. You can also do it of this. Make sure I did that right. Yeah. Right. You can imagine there are dozens, maybe hundreds, I have to do the math to figure out how many different combinations there are to get to 50%. That's why that 50% aggregate result is more likely, because there are more paths. There's only one way to get 100% black. So that kind of squares that circle. It explains, yes, in all likelihood, you are more likely to get that mean because you're more likely to choose a path that takes you there because there are more paths that get you that 50%. But it's possible you just get black a whole bunch of times. Right. We don't know what path it's going to take. We have to spin it. So don't be fooled. Any questions? let's switch gears in slightly and let's go reverse of this. How many of you are interested in stock market trading? Yes. Yes, so,
What are you asking?
I'm curious. Like, do you actually do it?
No.
No. But is that something you might want to do? How easy do you think it is?
I think it's a whole world of conditions to kind of immerse yourself in, understand the market trends.
A lot of information, a lot of interpretation. Do you think most people who actively trade, who buy and sell stocks every day, do you think that they typically do better than just than an average market return?
Day trading?
Yeah, day trading.
So much risky. I don't know.
But what do you think? Do you think that people who actively do it, because you're working a lot harder, you're actually looking at the information, do you think that they are more likely to what we call beat the market or make higher than an average return? No? Does everyone want to say yes or no to that?
I don't think they do. Like experts.
Yeah, like experts.
Yeah.
Like imagine some of the smartest people working on Wall Street, they have like 8 different screens in front of them, live information from all over the world. Are they, yeah.
I mean, even like when you're not around the outcome of make different choices, and people's choices are not stable, or how they want to invest is not.
So some stuff is just really hard to predict.
You can try. You can probably look at trends, of course, but at the end, it's not. There's not a 100% chance that you will always be correct, unless it's.
Oh, sure. No, I'm not saying. I'm just saying. On average, do you think that people tend to do better than the market? So I'm trying to compare it to someone who just puts money in the stock market and doesn't pay attention to it. You put money into what's called an index fund, it just diversifies, and then you walk away and you do nothing. You say no?
The person that's definitely evaluating more is going to be probably one of them.
Yeah?
No, I think they're both depends on the choice.
Why do you say that?
It's they're both putting money into the same stock market.
Well, one's actively trading and one's not. One's just sitting around doing nothing.
Well, that would probably be safer.
Sure. Yeah?
Obviously, the difference between the two is that a day trader needs to have a minimum of 25 grand into where does day trade, so they can do multiple trades in a day. Whereas the person who's not really looking at is only doing a couple trades maybe a month.
Yeah, so maybe the day trader is doing a lot more and is maybe more invested and knows exactly what's going on, has more information about not just what's going on in the market, but also like how the mechanics of it work and the things they're looking around for. While the passive trader, passive investment, literally doesn't pay attention at all.
Yeah, they have bigger risk, of course, but obviously they trade up to that, so they're making, they're not making more.
Sure. Sure. So maybe. Right. One last comment on this, and I'll tell you the answer.
It's kind of the same concept where they could both have likely chances. It's not like they're unfair or unfair thing. They could probably both have resources to the same knowledge and data, but one is more likely to maybe get more ahead or get more involved because they are being consistent compared to a person that isn't doing as many investments. Back in the day, they probably do have their own communication, but again, both the same.
Yeah. You think that maybe at some basic level that the person who has all this information and all this skill and knowledge will probably do better. That's essentially what the gist of what you're saying. And that's what a lot of economists thought. And then we actually looked at the data, and it turned out it's not true. On average, active traders don't beat the market. They don't make any more than people that just put money in an index fund and sit and forget about it. And the reason why is because, yes, the day trader has more information than the typical investor. The day trader is not competing with the passive investor. Who is the day trader competing with? Other day traders. And so it's not enough to say the day trader is smarter than the passive investor. Instead, the day trader is smarter than the other day traders. And that's not really the case, right? There's a lot of smart people. They have a lot of equipment. They have a lot of information. And then it's just a matter of who sells the stock first when the bad news hits, or who buys the stock first. You don't really know. Essentially, it's random, right? Sometimes they will have good years just by random results. And sometimes they will have bad years by random results. Here's where the statistics come in, because people will see the good years and they will assume, oh, this person knows what they're talking about. Right? When in fact, you're being fooled by randomness. Just like the person here for gambling policy saying, oh, red hasn't come up very often, therefore red is due. This is kind of saying the opposite, what someone suggested. Oh, black has come up a lot, it must be really good at coming up, right? When in fact it's random. This person does really well, when in fact it's random. Yeah?
Is it kind of the same idea of like, what goes up must come down, so if the market's slow, it's gonna have to come up again at some point, or if it's high, it's gonna have to go.
Yeah, it's kind of like that. So, I mean, this is kind of getting off topic, but in economics, we have this thing called the efficient market hypothesis, which argues that all information is baked into the price. So when you see the price going up a lot, you're like, oh, it has to keep going up. It's like, but everyone knows it's going up. So that idea of like, you know, it's doing well and it's on like this great course is already baked into this price. And the idea that it could fall because it's so high is already reflected in the price. It's really hard to beat the market. If you intend to go into day trading, remember, it's really hard. It's really hard. I don't really recommend it for anyone, but there are ways to kind of beat it, but it's more about being psychologically calm and not trying to outsmart one another. So we call this the hot hand fallacy. After basketball, because when someone is doing really well on the basketball court, making a lot of baskets in a row, we say, oh, that person's hot, or they're on fire, or they have a hot hand. They are more likely to make future baskets, when it could just be random. Another version of this, also from sports, is the Rookie of the Year in baseball. The Rookie of the Year is the baseball player that performed the best. That rookie rarely goes on to become a most valuable player. Rarely goes on to have an amazing career. In other words, they probably were just lucky that year. And a lot of people, they're at the top of the game, and the thing that determines who does better, it might be essentially random, much like stockbrokers, much like basketball players. I'm not saying it's completely that way, but people often attribute, oh, there's some skill, so that must mean there's no luck. No, there's some luck too. Leaving that over represented outcomes are more likely in future independent trials. So it's a flip side of this. Some people look at randomness and they assume, oh, the other thing that doesn't come up much must be due. Some people look at randomness and say, oh, that roulette wheel is really good at getting black. Therefore, it must be due because it's good at getting black. Let's keep betting black. I bring up the idea of this random element. Overrepresentation of the law of large numbers of da-da-da-da, because we are working with samples. And remember, all samples are what? They may be biased or they may not be biased, but no sample is perfectly precise, right? No sample is perfectly precise. All samples have some random amount. They might not be representative, not because there's bias, but just because of some random thing that happened. Just like, I flipped the coins. It might not have come out 50%, not because there's anything wrong with the coin or anything wrong with my flip, but because it's a random result. And I just might have randomly got more, randomly got less. So thinking in terms of randomness is a really helpful way to recall this underlying theme of the data. But once we have this sample data, we want to be able to describe it. And that's when we bring up. That's why we bring up central tendency. Central tendency is an umbrella way to describe the data. In short, it is a single number that captures the center of the data, of the sample data. It has three different versions, three different descriptors. You know them. They all begin with an M. What are they? Mean, median, and mode. What is the mean? Right, average. Mathematically, what is it? Oh, I would like to do this in some sort of notation, though. That would be nice, right? Like, rather than just write it out and add all the numbers up, can we do this using mathematical symbols? You know what? This is sigma, also known as summation notation. It's fun because it rhymes. Summation notation. It simply tells you to add up all the numbers you're about to see. What is xi? Anyone? Xi is the value of one of the observations in the data set. Also known as the ith observation. N, as mentioned, is the sample size, the number of observations in the data set. So what this is telling you to do is I equals 1, so look at the first observation, add it to the second observation, add it to the third observation, add it to the fourth observation, add it to the fifth observation, add it to the sixth observation, etc., 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 add it to the nth observation, and you're done. Add all the values together. It's just another way of saying adding all the values together, but in fun mathematical form. Fun. All right. And then we divide by what? Said it. The what? What is it? Give me one letter. N. Questions? Great. Median? Is simply the middle number. Half the observations are smaller. Half the observations are larger. If you have an even number of observations, then you just take the average of the two that are in the middle. Half the observations are smaller, half the observations are larger. And note how if you take the average of the two middle numbers, then that means half are smaller and half are larger. So it works out. Good? Oh, sorry. It's all in the note. And we know what the mode is.
The number that's distributed the most in the data set.
Most common number. Is the most common number. Let's go with this. So are we good on this? Does this seem familiar? I imagine a lot of you have had this before. Great. So then you can tell me, let's talk about US income. What do you think the mode is for US income? We'll make it household income, just to be fun. Anyone? What do you think the mode is?
National.
Yeah, national household income, the modal household income. Or if you want to make it hourly, we can make it hourly, however you want to do it. Yeah? Want to take yes? Hourly or household, it's up to you. I'll take anything. You think 50,000 is the modal income? Does anyone agree or disagree with Michelle? 50,000? You think less than that? What do you think, Barbara? Maybe 39?
The mode would be more or less than
Well, wait a minute. Let's be clear about this. When we say mode, we mean the most common number.
Right.
So, Michelle, that means that if somebody makes $50,000 and one, they would not be included. And if someone makes 49,999, they're not included. These are only people that make exactly 50,000. Or these are only people that make exactly 39,000. Does this seem like this is going to be really big?
Yes.
Maybe, but I can think of an income that's going to be that's more likely to be the mode.
0,
0 is one option.
or if you're like a, just around nice big number, like a million.
But yeah, so maybe, right? It might be that. I was also thinking
What?
$1.
Yeah, a lot of like rich people in the state of $1.
Oh, sure, like yeah, because they're running their like company and like, oh, just take $1 as my income. That's another one. So there's two ways to go about this. One is to what is the most common income in the United States for everyone? That's clearly 0, because there's a lot of people who don't work. Whether you are a stay-at-home parent, you don't work. Some full-time students don't work. My kids, who are 1 and 4, do not work. Right? Retired people too, unless you're counting like what they're taking out of retirement as income, which I think tax-wise they are, but they're not working, right? So if you think about the most common income, it's probably 0. If you only focus on people who are working, it's probably whatever the minimum wage happens to be. And that's going to be tricky because the minimum wage changes based on state. There's a federal one, and then some states have higher ones, and then some cities within states have even higher ones. But theoretically, it would be one of those numbers. That's why I said maybe we could do it in terms of per hour. Because doing it per year is harder because that's going to fluctuate based on person, based on how many hours they have. But an hourly wage might, whatever the minimum wage happens to be, that's the modal wage in all likelihood. Because again, maybe some people do make exactly 50,000. There's probably little spikes around that, but some people make a little bit more, some people make a little bit less, and minimum wage is probably the most common. Is that a good descriptor of the central tendency of income? What's the minimum wage in the United States? Well, what's the income in the United States? Well, the mode is the minimum wage. Is that helpful? No. Do you think that the people who make $1 less than 50,000 are that different than the people who make exactly 50,000? Yeah, they're basically the same, right? People make $1 more, about the same, right? So we don't necessarily, like, that's a weird thing about using the mode in this way. Is just looking at which has exactly that value. And that's fine if it's a categorical data. That's fine if there are not many values you're working with. It's not so fine for continuous data. So we know what a continuous value is? So how many different individual incomes are there? Right. Infinite. And in practical reality, though, only what, maybe hundreds of millions? Okay. So there are hundreds of millions of incomes, which means, well, if you were to plot that data, if you were to plot one number after another, even more than that, actually, because you would have to throw pennies at it, right, the cents. So maybe billions. It would be kind of smooth. It would be essentially a smooth function. How many GPAs are there? How many grade point averages are there? Remember, it's bounded between 0 and 4. How many are there? Nope. Is your GPA a whole number? Yeah. There are hundreds and hundreds. And if you want to go pure mathematically, there's infinite. Right? If you think about, take the decimal point out as far as you want. The decimal place out really far, there's an infinite number of GPAs. So this is also what we consider kind of continuous. It's not really working with whole numbers, and even if we do income as whole numbers, incomes really aren't appropriate for mode either. Mode is best for categories. Mode is best for categorical data. Maybe we can think of which is the most common income range. That's more helpful. Which is the most common class, middle class, upper class, whatever. That's more helpful. But mode is best for categories. Or small ranges. So if we were to look at what's the maximum number of doors on a house in all practical reality? What's the maximum number? Exterior doors. I think you might see more than 2 exterior doors on a house. Maybe the maximum. Maybe 5. Some house, I don't know, I'm thinking maximum, right? You have to think of a really nice house that has 5 doors on it. What's the minimum number of doors on a house? 1, right? Thank you. Don't say 0. You have to get inside. So we're talking 1 to 5. Can you have half a door? No, not. I mean, you can't, but then it's really a door, isn't it? It's an entry in the house. It's a way to get in. Full-size doors, right? You can't really have half a door. So if we're looking somewhere between 1 and 5, that's 5 numbers. Even though it's numerical, it's still, for our practical purposes, categorical in the sense of a modal number of doors is something that makes sense. It makes sense to look at. But for a lot of data, mode doesn't make sense. Though in a pie chart, you are looking at the modal value. You're looking at the biggest wedge. That's the mode. A more interesting distinction is between the median and the mean. And by the way, we call the mean also the arithmetic mean. We'll be doing the geometric mean next class. But the mean arithmetic mean. versus the median. So now let's do the same thing with income. A little higher, and it does the same job. 72. 72,641. So the years are not exactly the same, but given that this was in the past, this was farther in the past, you may be expecting to be 73, 74, whatever it is. This is higher. Why is that? Yeah.
There's others like really, really, really high incomes that are like hundreds of thousands, millions that are like driving the mean more that way.
Exactly. Those very large numbers, what we call outliers. Outliers are either unusually high values or unusually low values. The outliers drag the mean up. Think about it. Let's imagine this is the distribution of income. What's the lowest income can be? 0. You typically don't pay to work, right? The highest, well, as mentioned, there is theoretically no limit. The distribution might look something like that, where the median might be kind of over here, because keep in mind the median just simply divides it into 2 different sections. It doesn't look at the values past that. It only asks itself, is this more, is this less? But the mean actually looks at the individual values. So this person right over here, that's making $1 million a year, right, in their household income. For the mean, if that person made only half as much, $500,000 a year, would the median change? No. Would the mean change? Yes. One of the good things about the median is it sort of is not influenced by outliers. That outlier is treated the same if it was slightly above the median versus if it was way above the median. One of the bad things about the median, though, is that it's not influenced by outliers. It's a good and bad thing. Sometimes, if the richest people lost money, or the richest people are making money, making even more money, that won't change the median. That will change the mean. And it seems like that's an important change. You wouldn't detect it if you look at the middle number, but you would detect it if you look at the average. Median, not influenced by outliers. The median is not influenced by outliers. Not overly influenced. Overly. It obviously is influenced in something, the data is there, but it's not going to be disproportionately influenced. But you could argue it is proportionally because those values matter. So it's a distinction between, if you want to know what a typical salary is, you might look more through the median. If you want to know something more about what's the overall picture, what does this whole industry look like, you're going to want to look at the mean. If you're a restaurateur, you have all these tables in your restaurant. And you might want to know, what is the average check of the restaurant? Or the average check of the table? That's important, that you're looking at the average and not the median. Because if you look at the median, you're not including, or you're discounting essentially the people who make tons and tons of money, who might order 2 bottles of wine and a dessert and an appetizer. Those far extremes. But you want to include it because that is revenue for you. You don't necessarily care about the typical customer, you care about the average customer. if you change something about your setup in your restaurant, and the typical customer, the median customer doesn't care, but the high-end ones spend more, the mean is a better use. Because the mean looks at every value and considers every value of the data set, and directly incorporates that number into its calculation. In stats, when we are running numbers, when we are working with the data, we typically use the average. We typically use the mean, because the mean considers in detail directly the value of every number. But the median is also really useful. Like, there's a big difference between mean student loan debt and median student loan debt. Which one do you think, by the way, is higher, mean or median? Mean, why? Yeah, and who are those people that are 200,000 in debt? Doctors and lawyers. So it drives me crazy because everyone always reports the mean student loan debt. And the mean student loan debt is super scary. But the mean student loan debt includes people who are going to be making $200,000, $300,000, $400,000 a year, and that they just have a lot of debt because they just graduated from becoming a doctor or being a lawyer or something like that. And that's not really capturing the level of concern we want to capture. That's not really telling the full story. All right. With that in mind, I'm going to let you go. I didn't show you quite yet how to do this in Excel, but it's super fast, and we'll talk about it next class. I'll see you then. Have a great couple of days.